All right, sounds good. We can continue on. All right, welcome back. I just want to make a brief announcement. You know, it's the end of the conference, and we're ending about 4 o'clock today. So I thought people might want to get together and enjoy what Santa Cruz has to offer in terms of, you know, a drink or some company. So at the Humble Sea Brewery, which is on Swift Street, there's an address, 820 Swift Street, on the announcement page on the program. We'll just meet at 5 o'clock today for those who want to come and have a drink, and there's also a food truck. I have some room in my car. I can bring a few people down. I can bring you down there, but not back. You know, I'm very happy to do that. But if you want, please join us there at 5 p.m. today. Thank you.
And one other quick thing, I had a couple people comment about making plans for getting to the airport tomorrow. So it's not there yet, but give me 2 minutes, and at the bottom of the program, I'll put a link to a Google document where if you want to put your information and connect with each other to share a cab, share transportation, you can. But just to be clear, I'm not actually arranging things. I'll just make the document so you can contact each other. So 2 minutes or so, and there should be a link if you refresh the page. And now we can get started.
Okay, welcome back to the second session of the morning. Our first speaker is Sandy. Please go ahead. The stage is yours.
Thanks, Kartik. So speaking for myself, my goal over a long career in observational astronomy has been to explain the Hubble sequence. And of late, I'm suspecting that the physics of the Hubble sequence emerges rather late. And what I'm going to share with you is some evidence from TNG50 that points in that direction. So the substance of my remarks today are inspired by this diagram from a paper by Casey Popovich some years ago, in which he attempted to put together the precursors of the Milky Way based on mass matching. And I looked at this, first of all, I thought it was wonderful, and then I took a second look and I looked at discontinuities like this little thing and that big thing there, and I asked myself whether that could really be happening in the universe, and could, if it's not, could we use radii to constrain these mother-daughter relationships more tightly. So that's where I'm going today. We're going to use TNG50 as a guide, and we're going to use various parameters. So let me start by talking about some landscapes, X versus Y. This is, sorry. There we go. I better stop using the laser because I don't have enough neurons to use the laser at the same time. Okay, so this is on the y-axis, the central density, sigma 1 within 1 kpc projected stellar, and the stellar mass. And this is a plot of manga galaxies. And we see that it has some vertical width, and we've divided that vertical width into stripes, which we've called tracks. And for a long time, we've thought, well, maybe objects evolve along these tracks at late times. That would be described by the following plot. Okay, parallel evolution, no track crossing. Another possibility is that there is track crossing of a very special kind, namely this, in which objects start out being more similar and then diverge at late times, sort of the way the parts of a feather diverge at late times. And I'm calling that the sorting model. Something happened to them late which caused them to diverge. And of course, there's the possibility that things are much more chaotic than that they weren't very well organized at the beginning, and there's lots of track crossing, and I'm sort of calling that chaotic, chaotic sorting. So the gist of this is to figure out what a distribution like this means as far as galaxy evolution is concerned. So let's think about another XY diagram. The y-axis here is a measure of integrated star formation rate, and the x-axis is stellar population gradient. Could be color gradient, could be line strengths. And this new horizontal coordinate has emerged in our thinking about Sloan and Manga galaxies as an important additional parameter of galaxies that needs to be explained. And you can color this diagram by all kinds of intrinsic quantities. Here I've colored by stellar mass, and you can see patterns. And so we want to know where those patterns come from. Now, we can plot the track galaxies in this diagram and see that they fall along two different trajectories. And it's tempting to think that those are evolutionary paths. That's certainly one interpretation. We're going to come back to that in a minute. In the meantime, let me switch to yet another XY diagram, which is very important. And this is radius versus stellar mass. And here I've colored by this parameter sigma 1. And you can see that the relation is very tight. In other words, if you know the radius of the galaxy today and its mass, you can predict sigma 1 to high accuracy. So there's a plane here, and everything is closely correlated. And that means that essentially all the information that was available in the sigma 1 diagram should be available here. They should be interchangeable. And then it's interesting to say, well, what do the tracks look like that we just plotted in the other diagram? What do they look like here? And they look like horizontal motion. And so the first person to predict that galaxies evolve along essentially parallel tracks in this diagram was Van der Velde back in 2009. And this is kind of an attractive way of thinking about things because everybody has in their brain a simple picture of radius versus mass and the notion of evolving horizontally, whereas that other diagram with sigma 1, although it's interesting for quenching in black holes, is less intuitive. Just illustrating that the two are very similar, though. This is the star-forming main sequence. On the y-axis, the star formation rate specific, and then mass. This diagram colors by the original track parameter, and you can see that an evolutionary interpretation would be consistent, not proven, but consistent. Here, we might think that objects are evolving along these trajectories. But the point I really want to make is that if I plot the same diagram and color by galaxy radii, I get the same conclusion, okay? So that's my preamble, that's my introduction. And now I'd like to compare TNG with Manga in various planes that look like this. We've made many of these. I'm just going to show a few examples. This is the South America diagram, star formation rate here, color gradient here, in TNG and Manga. Forgot to silence my phone. Yeah, and we're coloring here by total stellar mass, just to illustrate. And what you're supposed to see is, in general, kind of similar patterns here. Red here, blue here, red here, blue here. Looking promising, not exactly perfect, but somewhat promising. Here's another one, same planes, but now colored by satellites. And satellites are more prominent on the left-hand sides of both distributions. Now let's change frame of reference and look at radius versus mass. And TNG50 is showing us the same sort of pattern versus specific star formation rate that we see in the real data. We're coloring here by star formation rate. And I think my last diagram here, we're coloring by sigma 1. And TNG50 reproduces the classic parameter that we saw earlier. Oh, one more diagram. This is half mass radius now colored by track. And the track parameter does the same thing in both the data and the model. Okay, so how well does Manga do with specific star formation rate versus mass? In other words, the star forming main sequence. Manga's on the left. Sorry, Manga's on the right, TNG on the left. Here's the star-forming main sequence. Here are a bunch of quenched objects. There are a bunch of quenched satellites in TNG50. These are supposed to be quenched by black holes. They don't quench very well. This is one of the big shortcomings of TNG50. It's not much better in TNG100. So I wouldn't recommend using these simulations to study black hole quenching, which is supposed to be their strong point. It really isn't. Okay, now we can color by something else. This is the radius of the mass within 90 versus the radius with mass within, of 20, 90, 20. And that's a good indicator of Cercic index. And we see that in general, the simulation is doing a fair job of matching the data, especially if we're willing to admit that these really should be quenched and lying down here if they were properly quenched. Okay, so all of this is promising. Here's a summary across the bottom. TNG50 shows enough similarities to real data to warrant using it to investigate the meaning of this track parameter and how it persists over time. Okay, so let's now look at the way objects evolve in the sigma 1 mass diagram. This is sigma 1 again, our central density versus stellar mass. And we're drawing vectors between the position of a galaxy at z of 1 and now. There are little arrows here. And this side colors the arrows by where the galaxies were at the beginning. So if you're at the top of the relation, you're blue, and if you're at the bottom, at the beginning, you're red. This, by the same token, colors by where you wind up. And we can see that this is much stronger correlation, and it's correlated with the recent evolutionary slope. And we can understand that. The reason for this, the explanation was pointed out by Joanna Wu and her colleagues, Sarah Ellison and Dan Walters. If a track is horizontal here, it means that's a red-centered galaxy that has a quenched bulge. And so it's rather flat, and it winds up having low central density compared to, this is the color gradient correlation that I was talking about before, and the opposite is true here. So these are our track 5 galaxies, track 5 having high density, low density, and the simulation says that we can create these tracks based on the way that gas falls in at late time, specifically the specific angular momentum. Low angular momentum, late gas makes these because it puts gas at the middle, and high angular momentum, late gas makes those. The gas falls into the outer parts, and so the middle looks more quenched. And here is the diagram that they presented to that effect. They actually plotted in the diagram individual tracks from z equals 0.5 to now. And you can see that these tracks are increasing in both coordinates, whereas these tracks are increasing at late coordinates. Okay, and we verified that. I showed this at the workshop last year. This track, now, we don't have to depend on models because we can actually plot real arrows for real galaxies. We have central star formation rates, which tell us, now I've done it. There we go. Good. Okay. We have central star formation rates, which tells us the rate at which the central density is evolving. We have integrated star formation rates, which tell us how this coordinate is evolving, and these arrows show you the relative slope. And no surprise, the red-centered galaxies have flat trajectories, and they're the ones that lie at the bottom. Okay? So Walters and Wu made a really nice point about how recent angular momentum could determine a color gradient, not yet investigated, but a reasonable parallel conclusion would be that lifetime angular momentum would determine galaxy radii. So I'm throwing that out as a speculation to you today. galaxy radii, it's important to understand them. Can we look in TNG and see that high angular momentum, specific angular momentum galaxies have large radii today, and the reverse, that's true. All right, so now let's look to see how consistent the track parameter is as a function of time. Y-axis is the change in this track number from z of 1 to now, and versus the track number today. And the best parameter I have found, single parameter to predict the distribution, the location of a galaxy in this plot, is the quantity that's plotted over here, which is the radial specific star formation gradient at an intermediate redshift z of 0.3. And if you think about it, the color pattern is exactly the way you would expect to make the tracks change the way they're changing. So another thing you can do with TNG50 is you can look at correlation coefficients between now and redshifts back in time. And here I'm showing correlations with the half-mass radius, the total mass, the star formation rate, on 100 megayear timescales and on gigayear timescales. All of those are available in our files thanks to the assiduous work of the people the collaborators who were listed up on the title slide. So what we see is, of course, there's perfect correlation with these quantities today, and the correlation coefficients go down as you look back in time. The best one is the correlation with mass, and that's why abundance matching works as well as it does. But RM50 also is significant, and this is suggesting that we could have improved Casey Pafovich's selection of mothers and daughters if we had taken advantage of radii, because radii don't change in TNG very rapidly between neighboring redshifts. By the same token, star formation rate decorrelates very rapidly, and that's consistent with reports by Sandro, Picella, and other folks about the short-term versus long-term variations. Jenny Wan actually spoke to that in her talk, and the numbers here in TNG50 agree with those statistics rather well. Okay, so I'm just reminding you of this picture and telling you that I think if we think about these correlation coefficients, we can make better versions of graphs like this. Further evidence that galaxies have attained their mature properties recently come from various directions here. It's now known that if we try to measure stellar population gradients from center to edge back in time, they start appearing around a z of 1 or slightly before. Disks began to settle dynamically at 2, but we're really getting cold around z of 1. And you know, in order to develop a color gradient, you probably have to have a cold disk, because if you have a hot disk, you're going to have the mixing of populations at different radii. So those two things go together. And then we have the shapes of galaxies. This is a study that was led by Haowen Zhang and Joel Premack, and they showed from studying shapes of galaxies that there's a significant contamination of prolate-shaped galaxies, even down to z of 1 at low mass, and they only disappear later. And we've had examples at this conference from Simons, the late formation of metallicity gradients, the pre-disk phase existing beginning at z of 1 in Fire 2 Milky Way simulations, and a late disk phase only as late as z of 0.5. In other words, simulations are also showing, some of them, that disk galaxies only settle late. And that's what we have found here, looking at the color gradient explanation. It's the arrival of the late gas with low or high angular momentum that's determining the color gradient. Okay, I'm almost finished. Let me move on now to an interesting extra additional topic in TNG50 that I think is really interesting. I happened randomly to make this plot, and I started with a bunch of galaxies here. This is half-mass radius versus stellar mass, and this is a selection of massive objects that sits in the upper left hand of the diagram. And I colored by star formation rate. And I could see that there's a correlation between the slope of the line and the star formation rate in that interval. I've put together several different intervals here for each object. So that's very intriguing because it's that correlation that we need, among others, to explain the change of Hubble types when we go from disk-dominated star-forming objects to de Vaucouleurs-dominated quenched objects. That's because it's believed that we're building up the quenched sequence here via a series of minor mergers which have steeper slope. And I asked myself, well, can we be seeing this transition here in TNG50? And if we do, can we study the physics of individual galaxies and figure out how it's happening exactly? So I proceeded to make the same diagram, half-mass radius versus stellar mass, and color by a whole bunch of different things. These are vectors to show how galaxies move between a z of 0.5 and now. And in this plot, I've colored by the total motion in the y-coordinate, and you can see a pattern. This colors by the total motion in the x-coordinate, and you can see a pattern. And finally, this one colors by the star formation rate in the middle of the interval, and you can see another pattern. So it's pretty obvious that something complex and interesting is going on here. Fishing around a bit to try to find a picture that summarizes this, I settled on the following parameter space. The y-axis here is the slope of the vector, and the length of the vector is the x-axis. Ignore the shaded region. Those are vectors that are so short that the slope is not very well determined. So just concentrate on the right-hand side of the diagram where the slope probably is more meaningful. And this plot colors the points by the star formation rate and verifies the fact that at a given value of the step size, the vector length, we're going from shallow slopes when the star formation rate is high to steep slopes when it is low. So this plot really summarizes the trend that caught my attention in the first place. And this one is the same xy coordinates, except now I'm coloring by the Sirsic index in the middle of the interval. And the Sirsic is again given by the ratio of the mass radius for 90% divided by the mass radius for 20%. Higher Sirsic is blue here. And again, if we take a cut at fixed step size, you'd see a very, very strong trend for steeper slopes when the Sirsic index is higher. So one of the great conundrums, I think, of understanding low redshift galaxy evolution is to understand how those parameters fit together. We see galaxies increasing their mass, their radii are changing, their Sirsic indices are changing, and at the same time, their star formation rates are going down. And those parameters are all correlated. I don't believe that anybody has a very full explanation of the structural changes as well as the star formation change, right? So I'm hopeful. Seems as though the necessary physics is present here in TNG50. It seems to be making correlations that are very promising. Perhaps we can unravel what's really happening, at least in this simulation, by looking at the behavior of individual galaxies. Okay, so here's my takeaway points. Very quickly, what do I really want to emphasize here? I think the first point is my most important, that the properties of galaxies today, many of them are of rather recent origin and should be studied at low redshift rather than high redshift. Angular momentum could be very, very important for radii and color gradients. And here's a list of good things and bad things about TNG50. And the list of good things is impressive when we restrict attention mainly to star-forming galaxies, not the quenching process. Thank you.
Thank you. Questions?
Hi, I'm Robert Feldman. Hi, Sandy. A very interesting talk. I wanted to ask you about the last point that you made about where you essentially show your color code by the specific star formation rate. And my question is, did you check or test somehow in the simulations whether these galaxies first change their star formation rate and then grow in size, or whether this happens the opposite way?
It seems to be contemporaneous.
Okay, so I think because if it was the opposite, where first the star formation rate goes down and then size grows, you could of course go back to dry mergers and all this kind of things, right? So this kind of picture. So that's why I was wondering.
Yeah. So in the data file that I'm working with, I have only rather widely spaced redshifts. The master data file has much more finely spaced redshifts. And your question, exactly what the relative timing is of these parameters, is a perfect, wonderful question. So, great question, and we'll look into it.
Okay. Maybe while we take the next question, the next speaker can set up, please. Thanks.
It turns out that thin disks start to appear 2 or 4 or even change your picture?
I certainly have to modify it. That's very true. Yeah.
Okay, maybe one.
Just a moment. I could then still ask if they're persistent. If I focus on what galaxies look like today, the appearance of a thin disk at high redshift might mean nothing. So we'd have to make a connection between what it did then and what it is now for the purpose of my question.
They may not be the same galaxies that persist, but the physical process that formed them may be similar, and that's the question.
Very good point.
Okay, sorry, I think we need to wrap up. We should take the questions in lunch. Sorry.